Okay, so let's get started then. I'm very pleased to introduce Yoël Perreau from Besançon, and he's speaking on embeddability of countably branching trees into quasi-reflexive spaces. Yoël, please go ahead.
Okay, thank you. So if you recall, we had a talk at this webinar a few months ago from Zhang, who introduced some new submetric characterization of the property beta of Rolevich. And the starting point of his work was some fork argument that came from an alternative proof of a result from Baudier, Calton, and Lancien, which is actually a purely metric characterization of property beta, but inside the class of reflexive Banach spaces. So in my talk, I will focus on this last result, and I will show how it can be extended to this larger quasi-reflexive setting once it is properly reformulated. All right, so let's get started. So let me introduce some very basic definitions and give some background about the result. So a map F is Lipschitz or by Lipschitz embedding if it satisfies the following inequalities. And equivalently, this map is Lipschitz one-to-one and has a Lipschitz inverse, okay? And yeah, the distortion of the map is then this product of the Lipschitz constants. Next, the map is coarse Lipschitz embedding if it satisfies the same kind of inequalities, but only for points which are at a certain distance from each other in the origin space. Okay, so points x and y in M, which are a distance bigger than this constant theta, this fixed constant theta. So the interest around that kind of embedding, nonlinear embedding, came from the study of local properties of Banach spaces and from a very famous rigidity theorem from Ribet. So if you have two Banach spaces x and y, and if x coarse Lipschitz embeds into y, then actually x is what we call crudely finitely representable in y, meaning that there is a uniform bound on the linear distortions of the embeddability of all the finite dimensional subspaces of x into y, okay? And yeah, some direct consequence of this result is that all the local properties are stable under coarse Lipschitz embeddings, meaning that if some Banach space Y has a local property P, and if another Banach space X embeds coarse Lipschitz into Y, then X also satisfies P, right? So some linear properties admit stability under nonlinear embeddings, and this kind of hints that it could be possible at least to find some purely metric objects that could characterize the properties. Okay, and the first result in this direction, also well known from Bourgain, states that Banach space is super reflexive if and only if the family of binary trees does not equilipschitz embed into it. So it does not embed with a uniform bound on the distortion. Okay, and with the terminology from Ostrovsky, we also say that this family Bn is a test family for super reflexivity. Okay, now the result from Baudier, Calton, and Lancien was an attempt to find an analog result to Bourgain's theorem in the asymptotic theory, and it is the following. The family Tn of countably branching trees is a test family for beta renormability inside the class of reflexive Banach spaces. Okay. Now it's known that property beta implies reflexivity, and it's actually equivalent to reflexivity, asymptotic smoothness, and asymptotic convexity. But we don't really know, or it was not known at that time, whether this second condition, this non-embeddability of countably branching trees, was a condition that could force reflexivity, right? So in other words, it's not clear whether this metric characterization of property beta, which is reflexive, could be extended to a very general setting, okay, without any reflexive assumption. And actually, I will show that this is not the case, because we will see that the James space, which is non-reflexive, does not contain this family of countably branching trees. So this is not metric characterization for beta outside of the reflexive world. All right, so let me start by recalling briefly some things about trees and about the Schlenk index of Banach spaces. Okay, so trees, countably branching trees, I think the easiest way to look at them is to think at them as graphs. Okay, so how do you define them? You start by a root, okay, a base point. Then on top of this point, you add countably many new points. And if you want to define the next level, for each of those new points, you add again countably many points, right? So this is the image of the tree, and this is a graph, and you can consider the usual graph distance or short path distance on Tn. But actually, there is another way of looking at the distance, which will be kind of easier for computations, which is to define an ordering on the tree. Okay, so sort of ordering between sequences, and then looking at this classical notion of ancestor and successors. Okay, and once all this is properly defined, you can get this formula for the distance. Now, the easiest way to look at the embeddability of these trees into Banach spaces is to consider these very simple examples of L1 and C0 embeddings. So I think, yeah, they really help to get a good grasp on how this metric is going. So just, I just want to show you how this little L1 construction goes to give some ideas. So instead of looking directly at little L1, for convenience, you look at this L1 of Tn. So this is all the families of real numbers indexed by your trees, which satisfy this L1 norm condition. Okay, and so then this will define the norm in L1 Tn, and this is a Banach space, and actually it's isometric to little L1 itself, right? Then in this space, we introduce the standard unit vector basis ES, okay, indexed by trees, and you consider this map F, which consists at for a fixed point in your trees, summing along the branch of the tree all the corresponding elements of the unit vector basis. Okay, so you make some sum along branches. And yeah, it's an easy exercise, but you can check that thanks to the metric, the tree metric, this is actually an isometric embedding. And a small remark, but which is also of interest for later, is that if you consider this kind of dual functionals, G, then this is a normal element in the dual space, and yeah, it's normal for F. Okay. Okay. So very briefly, a quick reminder on the Schlenk index of Banach space. So this is a very well-known object. Actually, this is an ordinal which is defined by measuring somehow how fast a certain inductive procedure happens in the unit ball of the dual space. Okay, so I don't want to go into details, but yeah, this is a very standard object, and it's closely related to asymptotic properties of Banach spaces through several ways, and in particular through this very important result from Knausthal and Schlumphecht. So if you have a separable Banach space, then the property of having a Schlenk index less than omega, where omega is this first countable ordinal, this is actually equivalent to PAUS renormability for some P. Okay. And just to complete the picture, in the reflexive world, you have a complete duality between this asymptotic convexity and asymptotic smoothness, which is probably also well known. And with this in mind, you can give this, in fact, original formulation of the theorem from Baudier, Calton, and Lancien. So a Banach space satisfies both that his Schlenk index and the Schlenk index of its dual are less than omega, if and only if it admits an equivalent PAUS norm and an equivalent QAUS norm. And in fact, you could even ask for one norm, which would be both AUS and AUC. This is just some technical thing. And yeah, finally, this is equivalent to this non-embeddability of the family of countably branching trees. Okay, so with the preceding slide, there is kind of two implications that remain to be proved in order to get this full cycle. The first one, this is this 3 implies 1, which is based on properties of the Schlenk index. And the second, this is this 2 implies 3, based on either on property beta or on this AUS AUC nodes. Yeah, just let me just give a very quick idea of how this first implication goes. So in fact, it comes from the fact that the Schlenk index in the separable case is linked with the existence of some specific trees in the unit ball of the dual space. Okay, so just to remind you, a tree in a Banach space, this is simply a family of elements of the Banach space, which is indexed by the trees. Okay, and we say that it's Wicksternal if, so for convenience, the root is sent to 0, and then all the nodes in the trees are Wicksternal sequences, meaning that if you fix any element S, which is not on the last level, then you can consider all the direct successor of S. This is this kind of notation here. And you ask, you want some constraints that all these sequences are Wicklinear. Okay. So the result is the following. If you have a separable Banach space, and if you have this property that the Schlenk index is strictly greater than omega. Then there is some constant epsilon uniform such that you can find in the dual space weak external trees whose norms of the elements are all greater than this small epsilon, and such that each time you take some along a branch of this tree, you stay inside of this unit ball. Okay, so when the Schlenk index of your space is big, you can kind of compress weak external trees into the unit ball of the dual. And once these trees are defined, you can go to the embeddability result. Okay, if you satisfy this condition on the Schlenk index, then actually the family of countably branching trees embed equilipshids into the space X and into the dual space. Now, how do you do that? So you consider the trees from the lemma, and you apply some kind of major-like procedure in order to construct a bounded tree in X, which will be almost bi-orthogonal to the tree in the dual space, meaning that if you apply a functional of the dual tree to the corresponding element in the space with the same indices, you will get 1. And if the two indices are different, then you will not get 0, but you will get something that is rather small and that you can control. Okay. And once you have those two trees in the space and in the dual, you will simply kind of mimic the two basic examples of L1 and C0 embeddings, and actually, you will get the embeddability. Okay, and just maybe if you take a quick look at the preceding slides, this kind of fact of having a sum along branches staying in the unit ball of the dual kind of corresponds to this norming functionals that appeared somewhere in the proof of the basic examples. Okay, now there is kind of some further technical problem here, because actually it's not very clear how to do the same thing for the property Schlenk index of dual space strictly greater than omega, because you would kind of fall into the bidual. But actually there is a technical way of lifting the tree into X, and so you get this this complete implication 3 implies 1. Okay, and you can note that this part does not requires reflexivity. So reflexivity will come in the second part of the proof. Okay, and so in the following parts, I will focus essentially on proving how this 2 implies 3 goes, and how it is possible to go beyond reflexivity. So actually, at least as far as I know, there are 2 different ways of proving this this implication. The first one was already explained by Zhang in his talk, and it relies on this property beta. So just a quick reminder, a norm has property beta if the separated sequences in the unit ball of your space cannot concentrate in a corner of the unit ball, so they have kind of to spread uniformly inside of the unit ball, and this leads to this picture of a fork. You start with one point X on one side of your ball. You have a center which is 0, and then at the other side of the ball you have countably many sequences. And well, if your norm has property beta, then at least one of the points has to be closer to x than 2. So it has to bend somehow towards the point x. Okay, and yeah, then this leads to this fork bending lemma from Baudier and Zhang for Lipschitz embeddings from the fork into Banach spaces with property beta. And yeah, this very simple lemma allows to implement some kind of self-improvement argument, and yeah, to get the desired result. The family Tn does not Lipschitz embed into a space X with property beta. So once you have all the correct tools in hand, so this proof is very simple and elegant, but it relies heavily on property beta, which is reflexive. And actually, we don't really know whether, well, some equivalent property could be discovered outside of the reflexive world. So if you want to extend this result beyond reflexivity, you have to go to the more technical proof from the original paper from Baudier, Calton, and Mancien. Okay, so this non-embeddability result. And the proof, in fact, relies on property AUS and AUC, and on the idea that when a Banach space satisfies those properties with a power type, then you have some control on the behavior of Wick-Star null trees in your dual space or in your space. And more precisely, you have some kind of LP estimates for along branches of your trees. Okay, so before introducing those properties, let me just recall the standard AUS and AUC star properties. So we say that a norm is asymptotically uniformly smooth if you can find some control over sums of this kind on a certain subspace, which is a finite codimension in X, and a control from above by a certain modulus rho, which has to be negligible before T. Okay, this kind of thing. And on the opposite, we say that a norm is a UC star if you have a control from below. So this time, this is on a dual space, so you have to consider Wick-Star closed cofinite dimensional subspaces, and your modulus here has to be strictly positive. Okay, so just basic examples. Maybe the most important one for us is this last one. If P lies strictly between P and infinity, then actually LP is both PAUS and PAUC. And this means that you can take for the moduli some function, some constant time T power P. Okay. And the fact is that more generally, if you look at the Banach space with those properties, you kind of keep some LP behavior. Okay, so I forgot to mention this, but the reason why we introduce Wick-Star convexity instead of just looking at this standard AUC is because you have very general dual T result. So a norm is AUS if and only if the dual norm is AUC star. And if you only consider the AUC property, this is no longer true outside of the reflexive world. But what I wanted to tell is that once you have AUS or AUC star norm, you kind of have some estimates for trees by LP norms. So let's take a closer look to the first one. So assume that your norm is PAUS for some P. Then there is a uniform constant such that whenever you have a weak null tree in the unit ball of your space, or simply a weak null bounded tree, then in fact, all the branches of some full subtree considered as a basis have an upper control by the standard unit vector basis of LPN. Okay, and by a full subtree, I mean a subset of Tn which is isometric to Tn itself. Okay, so big subset of Tn. And yeah, then you have kind of the same thing for the kind of dual property. If your norm on the dual space is QAUC star, then you have the same kind of control, but from this time from below. Okay. So the idea then of the proof of Baudier, Calton, and Lancien is to work with a norm on the space which is both AUS and AUC in the reflexive setting, and to use the two controls from above and from below in order to show that yeah, there is no way of embedding the trees into the space. So let me give a more detailed sketch of this proof. So the result is really way more technical than the well, the elegant proof with property beta. And yeah, some computations are very difficult and tricky, and it's very, yeah, it's kind of not very natural. It's difficult to really grasp what the geometrical ideas behind this are. So yeah, I just want to explain the kind of the procedure behind the proof, and yeah, I will hide all the technicalities in order to stay as simple as possible. Okay, so first step, we will do the proof by contradiction. So you use all the renorming tools that you have, so that you can assume that the norm on your space is both PAUS and QAUC for some P and Q. And you can also assume that your space is reflexive, no, not reflexive, separable, sorry. And then you will assume that your trees embed into the space, okay? Now, you want to apply somehow your tree estimates from the previous slide. So you want to obtain, in a way or another, weak star null bounded, no, weak null bounded trees, right? So this is the second part. This is, yeah, kind of a standard procedure. So you fix the height of the tree, and then instead of looking at the tree itself, which is not bounded, or not bounded independently from n, at least, you consider this this function z, which consists in looking at the difference between two successive levels. Okay. So by these Lipschitz inequalities, you get a bounded tree in X, and then you can use this reflexivity assumption to inductively apply weak sequential compactness in your tree. So at each level, you extract in order to get a weak convergence sequence. And once this is done, you kind of look at further differences to get weak null things. And so you deconstruct the original tree into smaller pieces, weak null pieces, which allow to reconstruct the tree, okay? By simply this formula here. If you sum on all the indices, then you go back to the original tree. All right, then you have to introduce some block functions, those functions W, K, R on the smaller trees. So the idea is that whenever you fix a branch, just to fix the idea, then you cut it into several parts, okay? And for technical reasons, you choose those parts to be exponentially decreasing. So you start with big parts at the top of the tree, and then those parts get smaller and smaller. And yeah, the contradiction will come by estimating this quantity here, this double sum of the norms of those block functions in the space X. So just in a few words, how do we do that? Well, you have to use these tree estimates from before. And actually, this right side inequality is quite straightforward because, yeah, this is just some lower LQ inequalities and then Helder in order to get this kind of thing. Plus this, of course, this reconstruction. Okay, you can when you sum the W, you also find F. So this will give you this nice right side inequality. And really tricky part is this second sharp inequalities, where you kind of have to do some kind of combinatorial reordering of the indices in order to estimate very sharply this whole quantity. Okay, but this is yeah, this is tricky and quite difficult to understand where all that comes from. And yeah, once this is done, yeah, you can easily see that this leads to a contradiction. You simply have to let M grow, and yeah, this will conclude the proof. Okay. So just some remark maybe before continuing. Where does this reflexivity assumption appears here? This is really this first part. No, the second part, sorry. This deconstruction of trees for which you have to extract sequences in a weak sense. And of course, this is only possible if you are working in the reflexive setting. So if you want to use this kind of methods to get something outside of the reflexive world, you kind of have to go around this obstruction. Right? So just a few words about the strategy for this. So there is a natural idea to go around this, is that instead of embedding your trees into the space X and using your weak sequential compactness, you could embed them into the bidual space on which you always you always have weak star sequential compactness. Okay, so this is yeah, very natural idea, but then the problem is that you could potentially lose the nice inequalities, tree inequalities that you have on the space X. Okay, you don't know whether those upper and lower tree inequalities will hold in this setting for weak star null trees. Actually, one of the estimates extends very well in this setting, and it's not problematic at all, because this this assumption that the Schlenk index of the dual space is less than omega, it actually creates a norm on the bidual space, which is a dual norm, and which is AUC star. So you directly get lower LQ estimates for weak star null trees in this bidual. And maybe just a word of caution. I think this is an interesting thing, but this norm, which is an equivalent norm on the dual space, should not be a dual norm, actually, because it is known that if a bidual norm on a space is a UC star, then actually it forces the space to be reflexive. So this is something you have to keep in mind. The norm you consider, it's a dual norm, but it's not a bidual norm. Okay, but it does not really matter for the proof, but yeah, then the really big obstructions for an extension, this is this question of upper estimates for external trees in the bidual. And actually, there is no reason in full generality that you can hope to obtain such estimates. And this is actually where this quasi-reflexive setting will appear. Okay, so the idea of working in the quasi-reflexive setting comes from a paper from Lancien and Haha, where they extended some previous results from Calton and Randriana Rivoni about some concentration properties of Hamming graphs into the reflexive setting to the quasi-reflexive setting. And actually, they discovered a very simple but very useful lemma, which is the following. If you have a norm on a Banach space, which is AUS, then actually, without further assumptions, you have a stronger property, which is that not only you have a control of this norm of sums into the space, but you also have some kind of control into the bidual for some Weak-Star closed cofinite subspace, provided that the base point somehow X is in the space X. Okay. So there is some hope that somehow if the trees that you get in the bidual space are close enough in some way to trees in X, that those upper estimates could be applied to them. And so one of the ideas to get this kind of thing is to use a concentration theorem due to Ramsey, and which says that if you look at trees into compact metric spaces, then actually the diameter of the tree always concentrates on some full subtree. Okay, so if you look at the distance between two elements, it's small on some full subtree. Okay, now this is great, but of course you have to get some compact metric spaces, and this is actually why you look at these quasi-reflexive spaces, which are defined as spaces whose bidual is decomposed as a sum of the space X itself and some other space E, which has to be finite dimensional. And yeah, the interest is that for those spaces, of course, the unit ball will be compact, and you will have you will be allowed to apply this concentration phenomenon. So in fact, if you look at any tree in the bidual of this sort of some quasi-reflexive space, and if you decompose it into a tree in X and a tree in E, then up to extraction, you can assume that whenever you look at differences in the bidual between two elements of the trees, then it's actually almost equal to differences between elements of the tree in X. And yeah, once you you have this kind of phenomenon. You can apply the lemma from l'ancienne Haha. So the idea is, as for the usual estimates, to kind of apply inductively your AUS property in your trees. So you start by the first level, you get something, then you go up in your trees, applying AUS and extracting successively in order to get estimates. And you obtain this upper tree estimates in biduals of quasi-reflexive spaces, which is just slightly different because you have, of course, to consider not only elements, but differences between two elements in the trees. Okay. And there is some technical issue while doing this, because in this inductive process, because of the differences, you kind of have to keep track of two sequences at the same time in the induction. This is this is problematic. And a way of going around this is to look for estimates, not for every pair of points in the tree, but only for a certain kind of pairs, which are those ones, the pairs which we call interlace. Okay, so you say that they interlace if you start with the first element of a sequence, then you have the second, the first element from the second sequence, and you continue like that to really interlace these sequences. And this kind of idea actually allows to kind of run this induction on this induction on two elements. Okay, and well, so you have your estimates now. Of course, this creates some further technical difficulties because when you run the proof from Odier-Calton l'Ancien, you have to take into account the fact that you have differences, but actually it works. You get the same kind of estimates, and so this gives this extension to the quasi-reflexive setting. So this condition on the Schlenk indices for quasi-reflexive Banach spaces is characterized by the non-embeddability of the family of countably branching trees. Okay, and once you have this kind of abstract result, you can apply it to a very concrete example, which is James space. So the James space is known to be quasi-reflexive of order 1, and it's also known that it satisfies these two conditions. You can construct some equivalent norm on J and on the dual space J star, which are AUS. And thanks to this general result, you get that the family of countably branching trees does not equilipschitz embed into this James space. Okay, and well, the James space is not reflexive, so actually by doing that, you prove that this second condition of non-embeddability does not force reflexivity. And this is kind of what I mentioned in the introduction. This Odier-Calton l'Ancien result is not cannot be a general metric characterization of property beta. And actually there I should mention, of course, the work from Zhang, where he found submetric characterization of beta, a very general characterization, and also recent work by Bautier and Gartland, where they actually develop a new notion of convexity and obtained a fully metric characterization of beta. in the general setting. All right, how much can I take a few more minutes for?
Yeah, sure. Still 5 minutes. Yeah.
Ah, okay, fine. Thank you. So I would just like to introduce another result from Baudier, Calton, and Lancien, which is a stability result. And yeah, I think there is some interesting question around this. So they proved that if X is a Banach space, and if Y is a reflexive Banach space satisfying the two conditions from the theorem, then if X embeds coarse Lipschitz into Y, actually it is reflexive, this is the first point, and then it has to satisfy the same conditions. So they got kind of stability result for this property under coarse Lipschitz embeddings. Okay, so how does the proof goes? Actually, so it's very different from the local case where you always have stability, right? In the asymptotic case, you don't know a priori whether this is possible or not. So they used their metric characterization in several ways. So first, this is maybe the easiest point, and this is linked, in fact, to the structure of the trees. You know that the trees, yeah, the points in the trees are kind of uniformly far apart because the distance between two different elements in the trees is at least one. So those trees are preserved by coarse Lipschitz embeddings. And so if your space Y satisfies the assumptions of the theorem, Baudier, Calton, Lancien tells you that the family cannot embed into Y, and thus it cannot embed into X, because if it would, then they would be transferred into Y by your coarse Lipschitz map, which would be a contradiction. Now, the second point is that this is something which has to do with Hamming concentration properties from Calton and Henry and Maribon. If X embed coarse Lipschitz into a Banach space Y, which is PAUS and reflexive, then the space X has to satisfy some Hamming concentration property with this power P. So I'm not going to define them, but the fact is that this property is actually forcing reflexivity. So if you combine 1 and 2, you know that if a space X embeds into space Y with the assumptions of the theorem, then X is reflexive and does not contain the tree. So again, by Baudier, Calton, Lancien, in the other implication, you get that it has to satisfy the same two conditions on the Schlenk indices. Okay, so now we obtained an extension of Baudier, Calton, Lancien to the quasi-reflexive setting. So I think it's natural to ask for kind of same stability result, but actually something is not working well in this, so it's really an open question. The problem in comparison with the previous proof is that it's not known whether you have this preservation of quasi-reflexivity under coarse Lipschitz embeddings, even if Y satisfies all these the necessary assumptions. And so just to give a bit more details, so you still have some Hamming concentration properties. This is a result from Lancien. This is actually the result from Lancien and Haha, this extension to the quasi-reflexive setting. So these properties are a bit different because you have to, again, to look at kind of interlacing sequences, and not full concentration. But you have something like that. But actually, this is a corollary of a very recent result from Fauvel. This kind of property, Hamming concentration property, does not imply quasi-reflexivity. And yeah, because she studied the stability of those properties under LP sums of Banach spaces, and she was able to show that, in fact, if you take an L2 sum of the James space, then it's not quasi-reflexive anymore, but it still has this this concentration property. Okay, and so yeah, things might really be different from the reflexive setting, and maybe we might expect some counterexample to this question for quasi-reflexive Banach spaces. Okay, all right. So this is all I wanted to say. Thank you very much for your attention.
Thank you very much. Any questions?
Yeah, I had one. Very nice talk, Yoël. Once you get past quasi-reflexivity, you didn't say what might be positive and negative. Is it possible the same results might hold if you assume that X double star over X is reflexive?
So we don't know, actually. This would be, of course, a very nice, yeah, a very nice improvement. And maybe, yeah, you could look at this kind of condition and add some further condition on, yeah, quotient being also AUS, and okay, having also further further asymptotic properties. But the problem is that there is no real way right now to replace this Ramsey concentration property. So it's not really clear what kind of tool we could use in this more general setting. But it would certainly be yeah, very interesting in itself, and also probably had some influence on other questions in the area, which are also kind of stuck in the quasi-reflexive setting. And we don't have any counterexample that would yeah, that would even without this this assumption, we don't know kind of anything. There are some natural spaces, like spaces constructed by Lindenstrauss, where you start from a separable space and you make some kind of James construction. You get a space which satisfies these assumption Schlenk indices, and for which the bidual, the quotient on from the bidual over the space is this starting space that you choose. So for example, if you choose like L1 of C0, you could expect maybe to get some kind of counterexample to embed the tree into X, but yeah, it seems it's not working so well, so I don't know whether it is possible or not.
A related question is, in your proof of the quasi-reflexive case, do you have to go through a higher dual, or you can do, does your calculation go through some K dual of the space? Like, because you take I think you take this iterated limits and stuff, right?
Yeah. So yeah, this in fact, the way to deal with those iterative limits, this is I think an idea that was introduced by Calton in some of his work. This is to look at those so-called Orlich norms, Orlich iterative norms, and those norms are yeah, they are key behind this idea of iterating yeah, those asymptotic properties.
No, what I meant was when I think the way you kind of have to work with this iterated limit is that you kind of want to, in your tree, you want to separate the elements. So you want to put gaps in between them. And so if the limits are in the space, then you can do it, right? Sort of, for example, that's why it works in reflexive spaces. This is related to Bill's question, whether you have to go through the, a higher dual being reflexive. So I was wondering if your calculation does that. Like, do you go through like a higher dual and then sort of separate the elements in the tree and use this estimates? I might be misunderstanding your idea, but that's what my guess how the proof was going. But
so the proof of this estimates are the induction is quite tricky because you kind of have to keep a very close track on how the quantifiers are applied. But I'm not sure I really understand what you mean by dual.
So when you have when you map your tree to your space, right? So you basically want to get like an asymptotic sort of estimates on the elements, correct?
Yeah.
And in order to do that, so you have to take some limits and do some Mazur kind of argumenting, and sort of control the support of the functions. And to do that, you have to know that this weak star limits are in the space, right? So, and when you take the iterated limits, you end up with some higher dual of the space. And I think that's how Nigel's proof is going. Then he's able to control. He doesn't know where he ends up with which dual, but eventually at some dual, and then that's how the calculation goes. I was wondering if you go through the same thing, but I'm not sure. Maybe I didn't. Yeah.
I'm sorry, but I don't.
It's okay. Maybe we'll let somebody else.
In the direction, this is Gilles Godefroy speaking, in the direction which was opened by Bill Johnson, if you take a space which is B-convex, that is, which has a non-trivial type, there is an old result, it's even older than James' example, which I think is due to Davis, Figel, and Johnson. Bill can fix me if I'm wrong, saying that in that case, you have a finite index of non-reflexivity. That is, if you iterate the operation which maps X to the space X double star quotient by X, you reach a reflexive space, or if you wish, the space 0 in finitely many steps, which was a very nice result, which is maybe a little bit forgotten today. So the question would be, if you limit yourself to spaces with non-trivial type, that is, spaces which do not contain L1n uniformly, is there any hope to extend your results to this class of spaces?
Okay, so yeah, I don't know. I can't give an answer right now, but yeah, this would be.
That would be quite ambitious, of course, but maybe you have a counterexample already, or.
No, not in mind. But yeah, this is very interesting. I will think about it.
Well, I have maybe other questions if I can take a minute. There is one item in a more recent paper by, I think, Ted Odell, Jacques, and Thomas Lumprest. Maybe if Thomas is here, he can check what I'm saying, where they showed in a quite indirect way that a collection of spaces is actually analytic. It was, I think, boundedness of Schlenk of X and Schlenk of X star, but their proof was very much non-direct. I don't have, unfortunately, the exact statement in mind, but you with a little bit of time on the article, you will find it. And it would be nice to see whether this descriptive result can be obtained with your technique.
Yeah.
Maybe someone has a comment about this, or
I think I mean using BKL
yes.
you can show that so reflexive and Schlenk index of the space and the dual less than omega is what co-analytic.
Well, analytic would be better for me. Co-analytic, I mean, that is probably your Ridge Borel or.
Wait, so how did it go?
Might be better to check the article. I mean, I would not like to say something stupid. So
now, because if you can show something with this characterization, I think it's co-analytic. But you want analytic, right?
yes, co-analytic should be fine because reflexive is co-analytic. So
yeah.
Okay, well, better check this. I mean, again, I may say something stupid. I mean, I have one last question for Yoël, which is probably desperate, but so far you have everything for Schlenk index bounded by omega. Is there any hope to say something about other ordinals, say omega square being the obvious candidate? Is it totally desperate, or is there anything to do?
Yeah, I don't know. Yeah, I don't have.
I think Thomas, you're here. I think Thomas and Pablos they took care of the omega. I mean higher ordinals.
Okay. Okay.
Right. In the paper where they characterize reflexivity in terms of this like semi-embedding, and I think they have, if I'm not mistaken, they have an analog of the BKL theorem for like omega to the alpha or something like this with Schreier trees and things like that.
Okay.
I don't know if Thomas is still here and or Pavlos is the but from what I remember, I mean, you might want to check the paper, their Duke paper, but it's they had to go to higher ordinals to be able to at some point characterize reflexivity.
Okay, so this could be done. So I should do my homework. I mean,
yeah, I'm pretty sure it's there somewhere in the paper. It's a long paper, but yeah.
Okay, thank you. Thank you for listening. And thanks for this nice lecture.
Thank you. Any other comments or questions? If not, thanks again, Yoël. Very nice talk.